Again, good morning and welcome to, I lost track now of the numbers of weeks. So we are in unit or chapter 37. That's where we're starting. So it's a different topic altogether, okay? And the plan is, I don't know if you guys remember that or not, to introduce chapter 37 today. Then on Thursday, when we meet, we're going to basically review all the previous chapters, namely, what is it, 17, 18, 19, and 20. 4 chapters that we're going to go through to see the key ideas and how the exam would look like. So please come ready. Come this Thursday with any questions or things that did not make sense to you, or how to do the calculations and things like that, because this is going to be preparing us for the exam, which is a week from this Thursday. So that is basically how the plan was. So today we're going to introduce chapter 37, which is relativity. Then we're going to stop from doing that. We're going to meet on Thursday. The plan also on Thursday, since we have an extended time, is we're going to start with it until we get tired, okay? At least we're going to put in the first lecture. And then the lab also, we can extend to do stuff instead of doing the lab of the chapter 37, which is actually due, the due date for it has been extended way back in March. So you still have plenty of time to do that lab. And then we're done. Okay, so this is Thursday. Then after that, when we meet on Tuesday, we need to finish chapter 37. We need to finish this chapter, and Thursday is going to be your exam. Is this the plan that we agreed on last time? Yes?
Think so?
Yes.
I remember right?
Okay, very good. So today we need to introduce chapter 37. And one of you gave me a criticism, which is actually a very good one. I love this kind of input, honestly. And I will give you the rationale behind it, okay? And the person basically stated that sometimes I spend a lot of time explaining things and going into a little bit of details. And the reasoning behind it is, first of all, probably this is for some of you the last chance that you're going to have in a physics class. And second, honestly, and this is something that was actually, it's in me already. And because I was influenced by the school of thought of Mr. Feynman, where he believes, and actually a lot of people do, it's not just him, that the journey to the concept is probably more important than the concept itself. Because how did we arrive to what we arrived to? And this is what I'm trying to instill in you also, is the process of thinking. You really have to criticize and really have to approach with doubt about these things. You really have to convince me that this is correct, that this is so. So this is basically the approach. And sometimes when I'm solving problems, especially, I take a lot of time in looking at it from different perspectives. But there are 6 steps in solving every problem that you really have to do, okay? And this, I'm trying to also do them through solving problems. First thing is, you need to read the problem. If you don't understand the problem, there is no way you're going to solve it. So you really need to read it. And as you read it, you gather information. So this is basically collecting information. And the information that you're going to gather is from the problem, sometimes explicitly stated. The mass of such and such object is this much. So this is explicitly stated. There is no interpretation for it. And sometimes it's inferred in a sense that we're going to be using this law and we're going to use this geometry. So there are some mathematical relationships that are implied in there. So they don't tell you specifically that the object probably has an initial velocity equals to 0, but they tell you start from rest. So you infer that V naught is equal to 0 and things of this one. So you really need to write those things that you know about the subject, either explicitly or implicitly. The second is, and actually while you're doing that, you're collecting also the questions that are asked. So you need to know what you're supposed to do, okay? The third process, the third stage, which is the actually combining these things and solving the problem, okay? I think there are a couple of steps, I put them together. But once you solve the problem, then you basically have answered the questions, okay? One key thing is to do dimensional analysis to try to see if the numbers make sense to you. If you find the speed that is greater than the speed of light, or you find something that doesn't make sense, you probably need to revise. So you really need to check your work also, which is another process, another step in the calculations. The final stage, and this is where I spend a lot of my time on it, is to discuss your answer. To see if it's really possible, what is its applications, what is the ramifications of this result, and things like that. That way, you have really a thorough understanding of the problem. And next time when you're confronted with it, to put it in the terms of, when confronted with a new problem, to put it in terms of what Mr. Feynman has basically used to say, is that, okay, we've shown you many ways of finding solutions to problems that we wrote for you on the book, or in the book, and things like that. Now you are in real life, you have a problem and you would want to solve. Hopefully with enough techniques and methods that you have developed when you're learning, you will find one or two that might work for you. If not, you're going to be inventing a new method that is probably a combination of one or more methods that you have already learned. This is basically empowering you to solve the real life problems. So this is the approach that I take in doing these things. And sometimes it's time consuming, but I'm hoping that the result, the benefits will outweigh the wasted times, or at least the length of time spent on these things, okay? We'll try to see how this goes down the road, okay? So that's good?
Yes.
Okay, very good. So again, we're starting a new topic. So why in the world do we need to start it? You always have to question these things. What's the reasoning behind it? I mean, did somebody all of a sudden wake up in the morning on the wrong side of the bed and invented something? Or was there really reasons for it? Okay, so we're talking about relativity now. So we're trying to understand where we come from. So let me share the screen. You probably have seen a lot of topics and read about it, and maybe watched movies about it and sci-fi stuff about it and all kinds of stories about it. And the idea behind it is we try to understand where this comes from. Let me put it for you guys so that you understand what you learned so far, okay? The biggest thing that you must have learned so far in all of your physics classes, not just this one, is this relationship. I mean, it's a vector relationship, but it's still only one law, really. If you think about it, everything you did in physics 1 was boiling down to this expression. In physics 2, let's put that aside for right now. Okay, I'm going to put this on the side for right now. In thermodynamics, the study that we learned, it's really boiling down to this expression also. Conservation of momentum, conservation of energy, all of this is coming from this expression, everything. Okay, it's coming from F equals to ma. So this is the cornerstone of everything. This relies on a very, very, very critical piece of information that we take it intuitively, that you and I, we think it's normal. Somebody is riding the train. Here is the train, okay, sitting on the train and jogging in the same time. The train is going 50 miles per hour and the person is jogging at 6 miles per hour. For an observer, for me, looking at them outside, I see that this person has a speed of 50 plus 6 in this direction, which is 56 miles per hour. This is intuitive. This is, we know it. I mean, and the theory behind it is easy, okay? If the person was running this way on the opposite direction with 6 miles per hour against the train, basically, if I compute the speed, I will find that it's 50 minus 6 is going to be 44 miles per hour. Why is that, you're asking? It's very simple. This is me, the observer O. This is my coordinate system X, not X prime, X, and whatever other units that you choose to. Let's focus only on one-dimensional thing. The train goes only on the tracks, so we're going to take that as the X direction. For the observer on the train, this is his reference frame. He's an observer called O prime, and he labels everything with a prime. So this is in another reference frame. This is the one that is moving with velocity u equals to 50 miles per hour from my vantage point. From the vantage point of this observer, he's sitting still. He is sipping his coffee. He's not moving, but he sees me going back on the station with 50 miles per hour. He sees me the one. For him, I am moving backward with 50 miles per hour. He sees the trees and the mountains and everything is coming rushing toward on the other side with 50 miles per hour. As far as he's concerned, he's sitting still. Okay? But for me, I can tell you that this person is actually moving with 50 miles per hour. Why? Because his reference frame is moving. Now, if he decides to move or objects in his location, he will label them with the coordinate x prime. So this is his x prime. From here to here is his x prime. That's all. This is his origin and this is his coordinates. For me, this is shifted in time with this much distance. Every second that passes is shifted by this distance. So what I say in this case is my coordinates x, which is for this same event, for this same object, and this is x, is simply clearly equal to x prime, whatever he gives me, plus ut. So you ask how fast he was jogging. According to me, his speed, which is v dx over dt, is equal to this dx over dt plus this u is constant. So we're assuming all along that the train is moving with constant speed. So this is a constant value no matter what. So this is, we're assuming that, okay? So when you take the derivative of ut, it's going to just pull a u in here. So if he was doing 6 miles per hour in his reference frame, because that's how he is jogging. I mean, you can jog probably for a normal person faster than this. So it's a normal speed. The train is moving 50 miles per hour. So as far as I'm concerned, this is how much he's moving, 56 miles per hour. But if he was moving with the negative speed, he was moving in the opposite direction, then his speed is in the negative direction. So I just subtract it and it's going to be the same thing. So this is the notion that the whole thing relies on, okay? This is called Galileo, and I'm sure he did this, relativity or classical relativity. Relativity. Meaning, from my vantage point and your vantage point, how we're interpreting things, okay? Here is the key though. If I want to find the acceleration of this object in this frame, if this velocity dx prime is not changing, I mean, it's changing, the velocity is changing. So that means that the acceleration from my vantage point, which is the derivative of the velocity with respect to time, is equal to this, his derivative of this velocity, and the derivative of the velocity, by the way, is the second derivative with respect to time. So it's going to be the derivative of this guy with respect to time, plus what is the derivative of this u with respect to time? What do you guys think?
1.
U is constant. So what is the derivative of a constant with respect to time?
0.
0.
Yeah, it should be 0. So we measure the same acceleration. Okay? We measure the same acceleration. Meaning, if I have F equals to ma in my reference frame, it's the same thing as his ma in his reference frame. It's the same law. So the laws of Newton would work for this observer as much as this observer, provided that u is constant. If u is not constant, then we have another term here, okay? Which is, have different names, centrifugal force for a rotation, and whatever you want to call it, okay? But at this point, this is true for both of us. For example, if I have a force of gravity in here acting in the y direction, and if I throw an object, for him, that object goes up and down. You're sitting on a train, and try this one, or in a car. I'm looking for a mass in here of any object. I don't have this. Okay, if I throw this up and down, and even if I am sitting in the train, I see it going up and down in the y direction. But for me, it's not going up and down. For me, because this is from my vantage point, from the observer O, this is going like this on a projectile. Okay, it's going like this because the train is actually shifting. Okay, but it's still, both of them can be described, whether the projectile or the up and down free fall is going to be described by mg, which is the force of gravity, equals to ma. Both of them. One of them has, for the up and down, has v in this direction equals to 0. That is his vantage point. But for me, it's a projectile that goes like this because v in the x direction, that is not equal to 0. And that's how you get a projectile. And both motions are the same. If we were to measure, for example, how long does it take to go up and down, the time of flight, we will find the same result. If we run an experiment for both of us to see the entire time where this one is suspended in the air, this is the time of flight, goes up and come back, we're going to find both of us at the same time. These two frames have a name. When u is constant, they're called inertial frames. Inertial frames meaning that the law of inertia works, meaning an object at rest in here, for this observer, will remain at rest forever and ever. If it was moving at constant speed, it's going to remain moving with constant speed in the same direction forever and ever, because it's under no net forces. The same thing for me. The same object, because now I know it has an initial speed, so it's going to remain with that speed forever and ever. If it was moving with respect to this observer with 0 velocity, so it's moving with respect to me with 50 miles per hour. And if it was moving already to begin with 10 miles per hour in one direction or the other, for this observer is going to retain that velocity of 50, either plus or minus that 10 miles. And it's going to be the same thing. So the law of inertia works in both of them. That's why they're called inertial frames. Okay. The law of Newton, F equals to ma, works for both of them, though, for these two inertial frames. Okay. So this is the foundation, really, upon which this theory is built. This is the classical theory of relativity. So it's natural that everything you did must satisfy these transformations. What is a transformation? Here is a transformation. Let me tell you what happened in physics too. And I know your instructor probably did not want to tell you that for one reason or the other. And even if I teach that class, I will not tell you that. And even the book does not mention that. We use that. We use F equals to ma for the cyclotron motion, for basically an object under a magnetic field going around circles, for the deviations inside an electric field and magnetic field, for the charges moving in a conductor. We use this law, really. I mean, everything with the drift velocity, when we average the velocities, we use F equals to ma in one form or the other, conservation of energy, whatever we use, is all boiling down back to this expression. However, Maxwell's equations, namely the divergence of the electric field, has to do with the charge distribution over epsilon naught. And I know that you guys used it in the integral form, whereas the circulation of EDA, not the circulation, I'm sorry, the divergence still is given by Q enclosed divided by epsilon naught. And that of the magnetic field is equal to 0 no matter what, because there are no monopoles. The same thing in here, the flux of the magnetic field over any closed surface is equal to 0. And the equation that gives you the curl of E equals to minus dB over dt. This is basically the law that is called Faradays Law, and the lens has the minus sign in it. Basically, it's the circulation of the electric field over loop, in this case, is equal to minus the rate at which the flux on the magnetic field changes with time. And the flux of the magnetic field is defined as this integral over the surface that is enclosed by that path of BDA. this surface cannot be closed. If it's closed, we're back to this relationship. So this is an open surface, okay? And this is Faradays law. Lens has that minus sign, and it's really a big deal. In other words, if the flux of the magnetic field were to change over a region, it will induce an electric field that circulates around the path that covers that region in such a way, if that electric field can create its own current, that current will create a magnetic field that will lead to a flux that opposes the flux that created it to begin with. It's a mouthful statement, all about the minus. The whole relationship that Faraday worked on was without the minus. Lenz added the minus, and then the other relationship of what is it? Ampere Maxwell relationship that gives you this equals to the current density times mu naught plus mu naught epsilon naught, the rate at which the electric field changes with time. Maxwell added this term because there was a flaw in Ampere's law, okay? And he made the case for it. And this is basically how the last relationship. Currents create a circulating magnetic field. This is stuff that you've learned in physics 2. This is everything really that you learned in physics 2. Everything else comes from these expressions. In integral form, this is similar to the other one where the circulation of the magnetic field, this is probably how you have seen it, is equal to mu naught times the current plus this term in here, which is mu naught times the rate at which the flux of the electric field changes with time. Okay, so this is all the terms that you have seen in, so this is in integral form. You spent a lot of time on the integral form. The differential form also are identical, okay? You can use Green's theorem or whatever theorem to convert from integrals back to differential forms. The problem with all of this laws, they don't retain, like F equals to ma retained its form. It's the same F equals to ma from both reference frames, from both inertial reference frames. And all of physics is expected to be the same. In other words, there is no experiment that you can conduct to tell me that you're moving or I am moving at constant speed. Okay? That's basically what this thing. If you apply F equals to ma and you tell me the time of flight for both experiments will be the same. The shape of the figure doesn't matter in this case. Both of them are actually the same figure if you do a transformation to one from the other. Okay? So in this case, there is no physics really. There is no experiment in physics that can tell if I am moving or you are moving, because you can always still argue that, hey, I am sitting still sipping my coffee and I'm sitting still in my chair. So how can you tell me that I am moving? I see you moving backward. I see the whole world is moving backward. There is no the only reason why we don't think that this is possible, that the train actually is stationary and the entire track is being pulled underneath of it with the earth, with the cows, with the trees, with the goats on the other side, is because this is a bias. Because we don't think that this is possible, that's all. We don't think that this is feasible, let's put it this way. But it is very possible also somehow that the entire scenery could be pulled from the train. And it's true that everything else is moving, but the train is not. So that's really the whole argument with it. These equations, though, do not retain their form. I think this is one of the homework problems, and we can work out the details why this is. They are not, they change from frame to another referential frame. What is it? Inertial frame. And this is a big problem. This is a big, big problem. Maxwell's equations, which are supposed to be very good equations, or supposed to be accurate equations, which are supposed to describe everything electricity and magnetism, they don't seem to be in compliance with the Newton's laws of motion. They don't seem to be in agreement with it. So that was a problem that physicists struggled with it for a long, long time. They didn't understand where the problem, where the discrepancy is, until Mr. Lorentz actually looked at these equations and he found different transformations similar to this ones, okay, that makes this possible, that makes this equation stay the same. In other words, if you have a charge attracting another charge, and you conduct, for example, the energy between them, you're going to find it the same in the other frame. But this transformation is better be different. Okay. This transformation do not work this way. We have to fix them. That was one problem. I mean, if you go back to these equations and put this equal to 0, that means there are no charges. And put this current density equal to 0, that means there are no currents. You are in free space. Free space meaning there are no charges. So that means the grad of the electric field is equal to 0, and the grad of the magnetic, which is always 0, this one. And the gradient, so the gradients, both of them are 0. And then the curl of the electric field is simply equal to minus the dB over the, this never changes because it did not have any external sources. This had charges in it that are 0 in free space. And the curl of the magnetic field now is only dependent on this term that Maxwell added himself. You do transformations. These equations are called the transversality equations, meaning that the electric field, as it moves, and the magnetic field, as they move, they're perpendicular to the direction of propagation. So that means that they're transverse. Transverse. That's why the electric field and the magnetic field, they're always perpendicular to the direction of pointing, the direction of propagation, which is actually has a name, which is pointing vector. Okay. Furthermore, these equations will give you back if you take a polarized wave in one direction. So the electric field is pointing in one direction, which is in the y direction, and the magnetic field is going to be in this case is going to be in the z direction because both of them are perpendicular to each other. And also at the end, the propagation is going to be in the x direction. If you work out all of these details, and I'm sure chapter 36 dealt with this equation, that's why I'm bringing chapter 36 because chapter 37 really relates to it. You will find an equation for the electric field, because now the electric field is purely in the x direction, and in the y direction, with respect to x is equal to 1 over term in here times the derivative of the electric field with respect to time. Okay, this term in here has a name. It's actually c squared is equal to 1 over mu naught epsilon naught, which is 299,972,358 meter per second squared. That's what C is. Roughly, this is 3 times 10 to the power 8 meter per second squared, or 300,000 kilometers per second squared. In other words, the speed of light turned out to be 300,000 kilometers per second. This is a review of chapter 36, basically, leading up to this topic. This is what you did, didn't you? Does this ring a bell? Yes, no, maybe?
Kind of.
Okay.
Yeah, it'll probably take some time.
Sorry?
It'll probably just be some review for me, to be honest.
Okay. So the point being in here is you end up with an equation which is called the wave equation. In other words, the solution is a wave, and that's the electromagnetic wave, the EM wave. Okay. B magnetic field and the z direction also satisfies the same thing. This is for a polarized wave. If it's not polarized, it's no big deal. Okay, just basically take the 2 components of the electric field and the 2 components of the magnetic field and work with them, and you'll get the circular polarization or the elliptical polarization, whatever polarization you're dealing with. If it's not polarized, just run it through a polarizer, and at the end you end up with this equation. Okay, and for the magnetic field also the same thing. There's going to be an equation with these terms in it. Okay, this is not compliant with Galilean transformations. Meaning if you have a wave, for me, the observer sitting in the train, if I have a perfectly electromagnetic wave with a given frequency, let's say, for example, it's the yellow light, okay, behaving properly on a laser beam, so I shine it, so I can see it's a blue, yellow light, no problem with it. I did the interference, for example, a Young experiment that you did in physics too. Everything looks beautiful. For the observer sitting outside in the station, he will find completely different. First of all, it's not a wave. The wave is destroyed. The color is gone. And you have all kinds of nonsense components in it. So it's not satisfying this wave equation whatsoever. So the laser beam now seems to be a mess. Okay? So that's what that means. It's a different physics altogether. So there is a distinction. There is a way for me to tell which one is moving and which one is not. If the yellow light for the laser beam retains its color and does the Young experiment properly and I have the different fringes of interference, then I am fine. I'm moving because you will not find the same sitting outside in the station. So there is a way of finding which inertial frame, and that is wrong. That cannot be if F equals to ma is correct, or if these equations are correct. One of them has to give. One of them has to give. That's what this whole thing. Either Newton is wrong or Maxwell is wrong. Okay, Maxwell has firm mathematics behind him. Newton relies on this relationship. All of his hopes are hinging on this relationship, if it's correct. Okay, which we take it for granted on the day-to-day basis. Furthermore, the speed of light is huge. That turns out from Maxwell's equations. 300,000, I'm roughing up the number, of course, it's slightly less than that, kilometers per second. This is tremendous speed. Compare that to the speed of sound. The speed of sound was 343 or 330 meter per second, depending on the temperature. It's temperature dependent. Okay? So at 0 Kelvin, it's around 330. At room temperature is around 343 meter per second. That means for sound, this is 0.3 kilometers per second. It's not even a kilometer per second. There is a big discrepancy between the two of them. The speed on a string, if you guys remember, standing waves on a string, turn out to be equal to the square root of the tension in the spring divided by the linear mass of the spring, basically how much mass you have in there. Okay? So it's even a smaller number than sound. Okay? Depending, it probably is going to propagate, depending on the tension though, depending on the linear mass of it. If you're playing music, you can do this calculations for yourself. Okay? Now, here is the thing about this relationship. Even this one, the speed of sound, as I was saying, depends on the temperature, because it really depends on the pressure, which is the bulk modulus for the medium in general. For the air, it's going to be the pressure in the air divided by the density of the material. In the case of the air, rho for air is roughly about 1.29 kilogram per cubic meter. Okay, so that's basically what this expression is. The bulk modulus for the air is going to be the pressure, the atmospheric pressure. So you can do the calculations, but that's actually dependent, because remember, the pressure is PV equal to nRT. It depends on temperature, okay? So there are all kinds of things in here, okay? And depends on the pressure, how sound is propagating. I mean, if you read more about the history of it, Newton made the calculation and assumed that the process is isothermal at constant temperature. Turns out the process is actually so fast that you cannot make that. It's an adiabatic process, as a matter of fact. And the calculation really gives you better results with the adiabatic process for the propagation of sound. Anyway, here is the general thinking about speeds of waves in general. They depend on some sort of a tension or material to stretch the medium. This is a string. This, for example, air. Okay, how you pull it together. The more you pull it, the faster the medium is. The more tension in it, the more you're going to have speed of the waves that propagate in it. Also, the less compact the material, the less the density, the higher the speed. Okay, so where is this wave propagating at for light? That was the question. So people made an assumption about a medium called ether is where EM waves propagate. That's basically the assumption. Ether then must have, look at the numbers, huge tension in it and extremely low density of it. So this is the properties of it, if it's true, or if it's this medium exists. High tensions, whatever it is, that tension, we don't know what it is, and extremely low, this is actually the inertia. The mass over volume is the inertia. This is the mass over length. So low inertia. Whatever that inertia is of that medium, but it must exist if this propagates in some medium, which we made the assumption for it. So this, the publication of Mr. Maxwell's equations was just before he died in 1877. And at that time, a lot of people, and he actually suggested an experiment to that effect on how to find the medium. And one of the suggestions that you have seen it actually in physics 2 is called an interferometer. I don't know if you remember that or not. You have a laser beam. Okay. And you have a, so you have a source, he didn't call it laser beam at that time, but you have a source of light. And you have half mirror, half reflecting mirror, I should say. Meaning 50% of the ray will go straight and the other 50% will go up. And they will meet a reflecting mirrors, both of them. And this is also a reflecting mirror. So as the beam that is transmitted will hit this reflecting mirror, it bounces back. And as the beam that hits it bounces back. And the two that come back in here, they're going to go to a point in here of observation. Okay, usually it's a plate. Okay. And the plate in this case, if the two beams are in sync, there will be no interference patterns. Okay, of course, the length of this point in here is L, and the length of this one is the same length, L. Okay, for our purposes. I know in physics 2, what you did, you placed the medium in here with an unknown index of refraction, and you adjusted the length of this one so that there will be no interference, and at the end of the day, you induce the value of the index of refraction. Does this, you guys remember this device? The interferometer? Yes?
No, not really.
I don't.
Okay, basically what it is it's toward the end of, I think, one of the chapters. I'm not sure if 35 or 36. You have a, you don't know what n is, the index of refraction of a material. So you place it in here. So because the index of extends lambda, so in this case, this distance extends to some extent by an amount that I don't know if I don't know what the material has an index of refraction. So it's extended, and there will be interference then, because this distance is different than this distance, clearly. So the waves in here will arrive with different phases, one of them different than the other. So what I do in this case, I adjust the length slightly up so that there will be no interference again. I don't see the fringes. I see again the same wave that started with. Okay. So in this case, because of the amount that I adjust with it, I can tell by how much the wavelength has changed in here, and I do simple calculation and find the index of refraction. So this is basically what you should have seen in physics 2 if you didn't do it already. Okay. So this is a device that was known. So it was known to measure actually the index of refraction. Without that, though, this was suggested to be used to find the velocity of Earth with respect to this medium ether. This is the idea. Okay. The beam that started in here is moving with the speed c. Plus the Earth, the entire Earth is drifting with respect to the medium, with respect to the ether, with respect to v. The entire apparatus being dragged in one direction with respect to the ether, okay? So that's the whole point of it. The beam that traveled in this direction with respect to the apparatus will have traveled with a relative velocity. Remember, if you have two cars moving one next to one another, both of them doing 50 miles per hour, their relative velocity is 0, because in this case, they're not moving with respect to one another. If one of them is doing 51 miles per hour and the other one is 50 miles per hour, the velocity with which it's overtaking, it's only 1 mile per hour. Is this intuitive enough? Yes?
Yes.
Yes.
Okay, so in this case, the wave that traveled this distance took this time, t1, which is just the distance, L, divided by the relative velocity in this case, with respect to the apparatus, not with respect to the external observer, which is c minus v. The returning wave, though, now you have two cars coming at 50 miles per hour on another. Their relative velocity is 100 miles per hour. I'm sitting in one of them. I'm not moving. My car is moving 50 miles per hour. And the other person is coming 50 miles per hour. So my relative velocity is going to be the sum of the two. Yes? Does that make sense? Yes, no?
Yes.
Okay. So it takes a whole time to go from the first beam, which is L over C minus V, and the second one, which is L over C plus V. Okay? Where V is that velocity that I want to find with respect to the ether. Okay? That is the first beam. The second beam, though, goes like this. Remember, the whole apparatus is moving with the velocity V. So it goes from here, hits the upper limit, and come back. Because the apparatus is moving with the velocity v, so let's call it takes time t2 now. The whole time is t2. So this distance is v times t2, because the apparatus is moving with the velocity v. The beam of light is moving with the velocity c. For this portion of going up, it's actually c of t2 over 2. And this is actually also coming down, because it's symmetry, of t2 over 2, half the time going up and half the time coming down. Okay? But the distance in here is just L. This is the same L as before. So half of this, which is v t2 over 2, is part of this right angle triangle. So using the Pythagorean theorem in this case, I can clearly see that c times t2 over 2 squared plus v, did I do a mistake in here? Times, I think there is something wrong with the calculation here. Okay, I'm going to fix it later on, okay? Is equal to L squared. No, it's what am I saying? That's why I don't know my Pythagorean theorem. Let's fix this one. The hypotenuse is actually C2 over T2 over 2. Okay, so C times T2 over 2 squared is equal to L squared plus V T2 over 2 squared. That looks better. Is this Pythagorean theorem? The adjacent squared plus the opposite squared is equal to the hypotenuse squared? Yes?
Yep, that's right.
Okay. Thank you, guys. Okay. So from here, we can find what this T2 is. Let's move it to this side. And we're going to find C squared times T, oh, sorry. C squared minus V squared times T2 over 2 squared. This is squared, by the way. No, it's not squared there. The difference squared is equal to L squared. I'm just trying to find the algebra in here of what T2 over 2 is. And it's going to be simply L squared over C squared minus V squared, the whole thing under the square root. And the L squared come out of the square root. And the C squared also come out of the square root. And I will end up with T2 equals to 2L divided by C times the square root of 1 over 1 minus V squared over C squared. Hopefully I didn't make any mistake in here. This is the time T2, it goes up and down. This is the time t1, it goes up and down. Obviously, there is a delay in time between the two of them, delta t, which is equal to t1 minus t2, and that is equal to the first time, which is, I could do the common denominator, and the common denominator is c squared minus v squared, and the numerator, so t1 is actually equal to L over c squared minus v squared times the numerator. The numerator is c plus v plus c minus v. So it's going to be 2c. And again, I can write this. This is just t1, by the way. So t1, I can write it as 2L over c times 1 minus v squared over c squared. So in other words, this expression is equal to 2L over c times 1 over 1 minus v squared over c squared plus or minus 1 over the square root of the same quantity. Okay. Probably I should, it doesn't matter, negative or positive, there is a delay. One is the, either earlier than the other, or the other one is behind the other one. So there is an interference in here. That's the key. And the interference depends on this ratio. As a matter of fact, if I use a Taylor expansion, this becomes 1 plus v squared over c squared, and this becomes minus 1 minus, or at least plus, I'm sorry, v squared over 2c squared. This is the leading term in the Taylor series. The half is coming from the square root, okay? So the 1 cancels the 1, and the v squared over c squared minus 1/2 of v squared over c squared. As a matter of fact, the delta t is going to be depending on the length of the parameter, depending on the speed of light, and depending on this term v squared over 2c squared. That's the difference between the two terms. The key point in here is, if I find interference, I find the difference in time, and from there I can find how far the Earth is moving with respect to the ether. When the experiment was conducted by both Michelson and Morley, working together, those are American, I think they write in, yeah, this name, and Morley, the experiment yielded the first time v equal to 0. There was no interference. So what they did was they rotated it with a 45 degree. There was v equal to 0. They rotated it with 90 degrees. Maybe this is where the Earth is moving, not this way. But that's going to give the same thing, except that delta t will be negative. And the only thing that's going to change in this case is because you're going to subtract that from the other, and you're going to get v equal to 0 still. So that was a problem. So what they suggested is, this is the day, this is your lucky day, okay? This is the day when the Earth was not moving with respect to the ether. Respect to the ether. That is like playing the lottery and winning from the first time, winning the whole thing. Your lucky day. Okay. Here is the thing, though. We know the Earth moves around its axis in one day. The radius of the Earth 6,400 kilometers. So the perimeter of the Earth is 2 pi times 6,400 kilometers. We know it does this rotation at 1 day. So I can find what's speed around this axis. In other words, what this apparatus is moving every day. So 6,000 kilometers divided by a day, which is 24 hours. An hour is 3,600 seconds. So this is in seconds. So I can find the velocity of rotation, plug in the numbers. It should give me 2 times, let me see what I'm doing in here. I know I'm not sharing it, but it's fine. I hope you guys can do the number in here because I cannot remember what this number is, honestly. 6,400 divided by open parentheses 24 times 3,600. And this should give me a velocity in kilometers per second, by the way, of, oh no, I need the number. I need this fraction here. Sorry about that. I need the decimal form. Okay, it gave me a fraction. 0.46 or 47 kilometers per second. Obviously, you could say the apparatus was not precise enough because this ratio depends on b squared over c squared. And this number over c squared is 3 times 10 to the power 300. That's 10 to the power 5. To put it in kilometers per second, the whole thing squared, remember? Obviously, this number is small, and the apparatus was not precise to this level. So forget about that, okay? Forget about the rotation of the Earth around its axis. We know the Earth goes around the sun. This distance is 150 million kilometers. 1 AU in 1 year. So multiply that by 2 pi and divide that by 1 year, which is 365 days times 24 hours a day times 3,600 kilometers, 3,600 seconds. So if I do the same calculation, this number will turn out to be roughly about 30 kilometers per second. The device was precise enough to pick up this speed. Okay? Because for a yellow light, as a matter of fact, you will find the wavelength difference between the wavelength and that one, because the wavelength is so tiny for a yellow light that the difference is actually going to be about half an oscillation. So you should see complete destructive interference for a yellow light if you take the Earth rotation around the sun. So all you have to do then is wait 6 months later and do the same experiment again. If this is the Earth moving this way, and it's moving against the speed of the ether, then these two speeds cancel, and that's why we got an apparent velocity of 0. So all we have to do is wait 6 months from today, when the Earth is moving this way, and it's moving also in the ether with respect to that way, and this effect would be doubled. So that if the device will be extremely precise, then even better, and it's going to give us big destructive interference. So we're going to see it, okay? So all you have to do is wait 6 months. Guess what? 6 months later, they did the same experiment and they found, again, no interference. Every time you do the same experiment, you find no interference. At that time, they didn't know that the Earth was drifting against the galaxy at even higher speed than this, which was about 100 kilometers per second. The Earth goes around with the sun, of course, drifting in space against the center of the galaxy at even faster than this. So it's still not being picked up, even with those experiments, and even with modern day experiments. So again, the entire galaxy is actually moving with faster speed. So we should pick up some speed at some point. That's my point. We're not picking up that speed whatsoever. This device, no matter how precise it is, and it's precise enough at least for the Earth around the sun, it did not pick up any interference whatsoever. So there was a problem. There was a problem, and a big problem. So we need to fix F equals to ma. That is really the problem. So from today, this law is no good. That is really where the whole problem is. And people struggled with this one because it's not easy to abandon a law, but it works at least for a lot of experiments. So it has to be replaced with something that explains everything that was done up to that point. In other words, the new law cannot really, for example, the projectile is still a projectile. It's going to always work. So if it did work under F equals to ma, it better also works under the new law. But the new law also, in addition, should explain what's going on in here. Why we're not picking up that speed with respect to the ether. So here comes Einstein. At that time, he was also around that time. He was working actually in Zurich. And he came up with two postulates. And the two postulates are the following. First of all, the laws of physics are the same for all inertial observers. In other words, Maxwell's equations are correct. Okay? And everything else also that we need to conduct, you cannot really distinguish between the two different reference frames. So this is postulate number one. The second postulate, based on this experiment, the speed of light is the same for all observers. The speed of light is the same for all observers. That's why you were not picking it up to begin with. If you shine a light in this laboratory, it's moving with the speed c. For somebody sitting outside of the Earth, looking at it going around the sun, is going to measure c also. Just because they shine a beam and you're moving on the Earth, that beam will go straight in the atmosphere. It's straight in the interstellar or at least planetary environment. For an observer sitting, for example, in Mars, you can see the same speed. He can measure the same 300,000 kilometers per second. Those are the two postulates of relativity. I want you to put this one in the discussion items as something to remember, because this is the foundation of this whole thing. Remember that Mr. Lorentz already came up with transformations that fixed. Helen, were you saying something?
Oh, what was the discussion item?
Is to restate this point, put them in your own words, okay? The two postulates. Yeah, the two postulates of relativity.
Restate the two postulates of relativity.
Own words, okay? Two postulates of relativity. So, the point being in here is that Mr. Lorentz already came up with transformations that make these equations invariant. They stay the same for all inertial frames. So these two postulates will help us rediscover those two postulates. Let me go back into the frames I was talking about in here, okay? So we have an observer, O prime, was measuring positions in the axis direction in the one-dimensional problem, okay? It's hard to do it in 3D for right now, but it's easy to generalize the idea from 1D. But I'm going to assume also that he's got a different time. And we'll see why that is. Because, hey, you want the two speeds to be the same for light, for the two observers. This one is measuring axis. And the other one is measuring x primes. Clearly, these two values are not the same, because this one is moving with respect to the other one with the speed u. So the two times must be different. Because if the ratio of the beam in here is x prime over something is fixed, x prime over something need to be c, and the other one is x prime or x over different thing or something equals to c. So these two things, which are the time really, cannot be the same. So if this is t, this better be t prime. In such a way that ratio is the same. If it is the same event though. If we're both measuring the same event, which is the speed of light, and that's what we're trying to do, then in this case, we must agree on the value of c, okay? This is the same for both observers. That is postulate number 2. So the times cannot be the same. So if this is t, and the other one is t prime, the times are not the same. And this is the key difference between the two theories, between relativity and classical mechanics. Mr. Newton assumed that there is a universal time. That's why he didn't change it in this expression. Where is it? This one. This is the same time. Both, if you wish, you can call it t prime, but you enforce that t prime is the same as t for both observers. They have the same clocks or synchronized clocks. They're everywhere the same clocks in the entire universe. So if they take, this one takes a second, the other one takes a second the same way. So that is basically the key difference in here. that Mr. Newton made the assumption that the clock or the time is universal. This cannot be true now. If we were to do an experiment for a special event, which is the speed of light, we better have, if the distances are not the same, we better have different times. Okay? So the transformation that we really need to be working with is the following. X, from my vantage point, is equal to x prime plus u and t prime, plus what Mr. Einstein called a fudge factor, a tinkering factor, if you wish, to fix things. Okay, so that things work out. What are the things that need to work out? These two postulates. One of them is the speed of light, and the other one is this thing works together. So now, from the vantage point of view on the train, you're seeing me moving. Actually, you're fixed, but you're seeing me moving with a velocity that is actually negative u. Okay, so from your vantage point, if I give you a coordinate x, you're going to say, okay, x minus u, minus my time t, the one I give you. This, you need to match it with your coordinates. And the tinkering factor need to be the same, because from your vantage point, everything is fixed except you're moving in the opposite direction. So if I allow for a tinkering factor gamma for me, then I must allow the same factor for you. Okay? This is what makes everything work out. Now, this gamma better be an even function of u. Gamma must be in such a way that gamma of u must be gamma of negative u. Because of this condition, the physics, whether I am moving and you're fixed, or you're moving and I am fixed, should be the same. That's why if I change from u to negative u, this gamma better be an even function in u. Or doesn't depend on you. Or gamma of u is constant. One of the two. Okay? So here is the deal. I'm going to take equation 1 and equation 2 and multiply them by one another. That's all. So I'm going to say gamma x times x prime, this is algebra now, is equal to gamma times gamma from both sides, which is gamma squared. My goal now is to find gamma. Okay, the tinkering factor. So I have x times x prime, the first term, x times x prime. I have plus ut prime times x, so it's going to be plus u x t prime. Okay, I have x prime. I'm exhausted the x, so now I need to multiply by the negative u, negative ut. Negative ut times x prime, negative ut. Let's write x prime first times t, okay, because always the spatial term first. And the last term in here, I have plus ut times negative ut, plus ut prime times negative ut. So minus u squared t prime. So that's all the multiplication that we have in here so far. We're going to do an experiment on light, special events. And this event is the following. We will allow you and I to do the following. When O and O prime coincided with one another, his was measuring x primes, I was measuring x, and he was measuring, I was measuring it at time t, and he was measuring it at time t prime. So this is the beginning. This is the start. At the start, we fire a laser beam. When t was equal to 0, or t prime was equal to 0, and x also was equal to 0, and x prime equals to 0. This is the start of the event, though. the end of the event is, so this is the beginning. The end, I'm stationary, so I'm standing still, okay? You are moving with the velocity u. So this is observer O prime, this is observer O, and this is x prime, and this is t prime, and this is x, and this is t. Now, the laser beam that we fired in the beginning must have reached this point. Okay? You measure the distance and you say it's actually x prime. This is the distance from here to here. You measure the time and you find it to be t prime. I measure the same things and I say actually that event is this distance, which is x. And I measure the time and I found it to be t. So this is the beginning, this is the end of the same event. So again, we multiply these numbers, x times x prime. By the way, when we do this, that means you're saying x prime over t prime is c. When I do this, I can say that c is actually equal to x over t. This is this event that we did. This is an experiment, if you wish, we did. This is a hypothetical experiment. The Duncan experiment called in German. Anyway, so it's clearly from this expression that x prime for light is equal to ct prime and x is equal to ct for light, for this special event. So again, we multiply these two numbers, x times x prime, and we find it to be c squared times t prime. This is a special event. We're going to take this equation 3 for that special event, since this is true all the time. So this is always. We're going to map it to this special event. So x times x prime is c squared times. So equation 4 becomes equation 5. So it becomes c squared times t prime. This is equation 4, by the way. I'm writing it. It's equal to gamma squared times the same product. So it's equal to gamma squared times c squared t prime, because that's the same product of x times x prime, plus ux times ct prime. And ux, x is ct. So plus u times c times t prime, because x is equal to ct, minus ux prime times t. And x prime is ct prime. So I'm going to sub the value in here. So it's going to be minus uc times t prime again, because I already had a t to begin with, and x prime brings another t prime, minus u squared times t prime. This does not have an x or an x prime in it. So it's going to be minus u squared t prime. Obviously, this cancels because they're the same term. And I will be left with, again, the t prime cancel, which is good because this is a hypothetical experiment. It's not, so no matter what when you conduct the experiment, these two terms cancel. So we end up with an expression for c squared equals to gamma squared times, I'm left with c squared in here minus u squared in here. And this is, we can give me gamma now. Gamma equals to 1 over square root of 1 minus q squared over c squared. This is the tinkering factor. This is the fudge factor, if you want to call it that way. Okay, it's actually called now a Lorentz factor, because it's the same thing that Mr. Lorentz has come up with to begin with. It's called Lorentz factor. Okay, and sure enough, it depends on, it's an even function in U, so it's not an odd function. So if you change from one observer to the other, gamma doesn't change, it stays the same. Okay, so immediately we can clearly see that for gamma to be real, that means that this number is less than 1. Otherwise, 1 minus something bigger than 1, we have a problem. So in other words, U is always less than C. This, nothing can move faster than light. Okay, this is a consequence of this factor. If we're going to do this thing, this better be true. So let's write them, both of them. So we said that x equals to gamma. Okay, for the case, for the sake, let's write it down. Okay, 1 over square root of 1 minus u squared over c squared times x. This is x prime, by the way, x minus ut, and then minus ut, and x is equal to 1 over the same factor, 1 minus u squared over c squared times x prime plus ut prime. Okay. Did I do it backward? I think I did it backward. So this is actually minus, this is the primes. And this is the prime. Yes? X prime minus ut prime. This is how we're supposed to have it to begin with. Oh man, I had it correct. No, that's correct. Sorry guys. after a long, x prime. Let's think about this minus and business signs. Okay, so this is x, and this is u, moving this way, and this is x prime. So x prime plus u. So this is a plus, and this becomes a minus. So I had it correct. Okay, so I had it correct to begin with, except that for some reason I messed it up when you start to overthink it. And this makes sense so far? Yes? No? Okay, here's the key. You need to redo the calculations, okay? That's another point. So redo the derivation. It helps you understand where these things are coming from. Okay? If you need to come back to this video and watch this thing going again. So we need to solve this equation or sub this equation here, and we will find an equation at the end of the day for t prime as a function of both x and t. So here is how we're going to do it. Again, x is equal to gamma times x prime. X prime is, so we're going to open the another parenthesis. So it's x prime is gamma times x minus ut, and the whole thing ut, and the whole thing is added to it ut prime. Okay. So I'm going to multiply gamma times this expression and move it to the other side, and it would have a gamma times ut prime. So I need to bring this term to the other side. So what I have in this case is x is equal to gamma squared times x minus ut. And then on the other side, I have plus gamma ut prime. So far, so good. All I did was sub the value of x prime into this expression. Okay. And here is the value. So I restored the value of gamma because I'm tired of writing 1 over square root of 1 minus u squared over c squared. Okay. So remember, gamma squared is 1 over 1 minus u squared plus over c squared. So I'm going to find what t prime now. So for that, I do T prime is equal to 1 over gamma u times x minus gamma squared x minus, so it's going to be plus gamma squared u t. So I moved it to the other side now, and I changed the signs, and I divided by gamma u. Okay. I have the second term is easy because I can cancel u with u, and I cancel gamma with gamma squared, then I will be left with a gamma t. So let's do that. So the last term is going to give me gamma t. The first two terms, though, are the following. I'm going to have 1 over gamma u times 1 minus gamma squared times x. What is 1 minus gamma squared? Remember, 1 minus 1 over 1 minus u squared over c squared. That's what that difference is. The common denominator is 1 minus u squared over c squared. I have a 1 times this denominator, which is 1 minus u squared over c squared, minus 1. So the minus 1 and the 1 cancel, and then I will have a negative of u squared over c squared. So what I ended up with is t prime equals to gamma t, the first term, and this divided by gamma u. Okay, I have to be careful with it. I have a negative sign in here. So I have a negative u squared over c squared divided by gamma u. U and u squared cancel. And then at the end of the day, I have an x in here. Okay. For some reason, I'm getting a result that is incorrect. Did I make a mistake, guys? Okay. Minus ut, that's correct. Plus ut prime, that's correct. Gamma times gamma x minus ut, that's correct. Plus gamma times, okay. When I moved it to the other side, I have a gamma squared times u times t, that's correct. And I have a 1 minus. Okay, I really need to think about this one. I think there is a mistake somewhere in here because this probably is going to give us the wrong answer. In other words, t prime is going to be gamma times t minus u over c squared times x, but there should not, I have a gamma squared in here, and for some reason I shouldn't have it, okay? That's where the problem is, okay? So the correct answer should be, and we need to fix this one in here, and I will follow up with you guys on it, okay? It's a mistake in algebra, and right now we still have about 5 minutes, and we need to fix this one. So t prime should be gamma times t minus u, as we have it, x over c squared, that's it. And x prime is equal to gamma times x minus ut, okay? So these are called the Lorentz transformations. So we have a problem in here in this expression, but some reason I am either I forgot to multiply by another gamma or something that we ended up with it. So one minus gamma squared is equal to okay. So I really need to think about where the error is coming from, okay, in here. But this is the correct result. I know them because I memorized them. So this is the Lorentz transformation. So we need to, I need to basically send you a I know the book, all it does, it gives you those transformations. Here are Lorentz transformations, okay? But the point in here, there is an issue with the algebra in here. Let's make it everybody working together on this. Here is a challenge so that you understand what you're supposed to do, okay? You have these two expressions. What are they? These two ones, 1 and 2. You have two equations with two unknowns, and the unknowns are x prime and t prime. Okay, the unknowns are x prime and t primes. You have two equations with two unknowns, and you would want to solve two equations with two unknowns. That's all. X and t are known. Okay, so once you solve for these two unknowns, x and prime and t prime, you should find this result. This is the solution for the two unknowns. In terms of the knowns, or you can treat x prime and t prime are known and deal with x and t are unknown. If you do that, you will find the following result. T should be equal to gamma times t prime. Remember, now we're solving for t, not t prime. Plus, so instead of minus, you're going to find a plus u over c squared x prime, and x equals to gamma times x prime, which is the same equation, that doesn't change at all, plus u t prime. Okay, so those are the two forms of Lorentz transformations. This is from observer O vantage point, looking at the coordinates of O prime. So if O prime provides the information to O, you use this expression. If O provides the information to O prime, you use the first one. This is also still Lorentz transformation, okay? All the difference between them is that wherever there was a prime becomes M prime. Wherever there was no prime becomes a prime. And then the sign of U change, that's all. So that's the rule for it. So whenever you see a prime, remove it. And if you don't see it, put it. And you change the sign, that's all. Same thing in here. Whenever you see a prime, remove it. And whenever you don't see it, plug it in and change the sign, and you will recover the others. So those are the Lorentz transformations. First of all, we need to fix this. So we need to get rid of this gamma squared that appeared somehow in here. And then also use these transformations for several conclusions. We're going to do the time dilations. We're going to do the length contraction. We're going to do the loss of simultaneity, which is extremely important for the lab. And we're going to do also the energy mass relationship, what you have probably read about, E equals to mc squared, and all of these things before we conclude with this chapter. Now, I hope that you guys will work on this problem and help me out in this case in here. And if not, I'll find it. And actually, if you look at the notes in the discussions, I think it's one of the videos I did in the past. You will find the correct derivation in there, but I'll put it for you guys in there to see it. This is known in physics, or at least a common problem in physics, when you do calculation, and if somebody else looks at it, they always find the mistake. If not, when you look at it again, you're going to probably repeat the same steps in it. It's known in physics as chasing after pi. So a common practice then when you do problems, after several pages of calculations, you end up with either a missing pi or an extra pi in the calculations. Pi, of course, can be anything, can be E, can be whatever constant, your speed of light, for example. You end up with either one less or one more. And this is exactly what happened to us in here. We ended up with an extra term of gamma squared that we shouldn't. So this is a known problem in physics called chasing after pi, okay? So I will see you guys this Thursday, and the focus there on Thursday is going to be on the exam. Any questions for me?
Professor Busidi, to be sure, for the discussion item, so for the last part that we did just now, do we have to redo the derivation? Is that part of the discussion as well?
it's a good idea to actually do it, and at least to be familiar with it, at least writing the Lorentz transformation at the final form, okay? Because they're extremely important to help us understand at least some of the homework problems. They rely on them, okay? And to understand what is next, okay?
Okay.
Yeah, I know the book throws in the transformations for you, but it's actually better to understand how they're interestingly connected to the two principles of relativity. And the two principles of relativity state that the speed of light is the same for all observers. That's why we use that special event where both observers measure the speed of light and found the same answer, although they are recording different times and different coordinates. And then also we use the fact that in this case, this term is the same, and it turns out to be actually a key piece in there. Okay, we're going to have more discussions about this one on Tuesday of next week. And hopefully today or tomorrow, I'm going to post the thorough calculation with this one, and we come back to it if in case to find where the mistake went and fix it quickly, okay? But we're going to build on this one. So to answer your question, yes, the two postulates of relativity plus at least show some understanding of what these two transformations are. The two transformations I meant with it is the ones I wrote the last toward the end, namely either from the vantage point of O prime looking at O, or from the vantage point of O looking at O prime. And these are actually the key piece of the puzzle, okay? Whether doing homework problems or actually, as I was saying, understanding the whole theory of relativity, at least this version of relativity, which is called the special theory of relativity, okay? Sounds good?
Sounds good.
Yep.
Everybody else? Okay, very good. So I'm going to stop the recording, and I will see you guys Thursday.